This is Megan Jones from ICEAA, here with Anthony March from SCAF, and we're welcoming you to the third of our 2020 SCAF ICEAA virtual workshop presentations. First up today is Carol Dekkers from Quality Plus Technologies. Carol is an internationally recognized expert on software sizing, heavily involved with both IFPUG and ISBSG. And I've had the pleasure of working with Carol directly in the past year on ICEA's upcoming software CBOC curriculum that's due to come out next year. And Carol is here today to present us the future of IT and software estimating. Carol?
Thank you, Megan. So welcome to everybody who's here from wherever you are in the world. Here in Florida today, it's a little bit chilly. So if you're in a place that you have a chance of frost, I know what you're talking about. So this is a somewhat of a reprise, but definitely an updated presentation that I did at the Ottawa ICEAA as a keynote last fall. So how much changes in a year? It was very nice to be in Ottawa, very nice to be part of the international ICEAA community. So I'll tell you a little bit about myself. My company, Quality Plus Technologies, we're based in the United States. We do consulting, training, and coaching, and you may notice that there are some familiar names here, but I've been in consulting for the last 25 years and recently traveled. Actually, my last major trip before COVID was to Malaysia, where I'm advising the government of Malaysia and some of the clients there on software cost estimation and sizing. A little bit about me. Megan was very kind with her introduction. I am a PMP, a project management professional, a certified function point specialist fellow, which means I've held that designation for more than 25 years. I'm a professional engineer. I got my training in Canada, and I relocated to Florida, this is actually one of my actual pictures. It's not a clip art or anything like that, 25 years ago. I'm the lead author, and I'm very proud to be the lead author of the ICEAA Software Cost Estimation Body of Knowledge, or Software CBOC. I'm a past president of the International Function Point Users Group. I've been a ISO International Organization for Standardization, ISO IEC project editor since 1994. Suffice to say, I'm learning a lot, and it's very interesting in the area of software cost estimation, just to see where we're at and where we've been. So wouldn't it be kind of fun to have a crystal ball to actually predict the future? Well, in 2020, I'm not so sure about that anymore, but to be able to predict the future of IT and software estimation. Let's kind of take a look at the past and the future of software cost estimation, where we've been, what's going well today, and what trends are kind of on the horizon. So just kind of come with me, we'll connect some dots between the world today and where we're actually going and headed with ICEAA and software cost estimation. So kind of crystal balls, roller coasters, and software. We'll talk a little bit about the basics, a little bit about models and some of the questions, trends, and then I'd like to get into introduce you formally to something I now almost consider my baby, but the software CBOC. And I'm hoping that you'll be equally excited as I am. So where are we in software? Where have we been in the past? Where are we today? Well, it's not all good news. If you take a look from 1998 to 2005, there were a lot of problems. And if you look at these different companies, you look at their issues that came up on some major software expenditures. So take a look at Hudson Bay Company. They had problems with their inventory system that contributed to a $33.3 million loss, which in today's dollars doesn't seem like that's that big. But the UK Inland Revenue, as many of you may be familiar with, in 2004-2005, software errors contributed to a £3.45 billion tax credit overpayment. That's pretty significant. So there's software errors, there's situations where the software doesn't meet the needs, or it's way over budget or way behind schedule. And this has gone on since we started collecting metrics on what constitutes good, bad, failed projects. But you know what? Bad cost estimates were not the reason that the projects failed. But when failure equals money, when people attribute that failure on a project is due to losses, major problems, deaths, it becomes a major issue. Software industry stats a decade ago. Well, let's take a look at some of those. And this comes from Galbraith. So there were Standish findings updated, 10 years ago. 80% of technology projects actually cost more than they returned. That's not great. Oxford University looked at IT project success and did a study, and they said, only 16% were deemed successful, and 74% were deemed challenged, and 10% were deemed abandoned. British Computer Society did a study that was similar to that. National Institute of Standards in the United States did similar studies. Everybody's doing studies on what's going wrong with software, and it's not really good news. The DoD, as recently as 2011, reported that 40 to 60% of the work that we do on software projects is actually rear work, which means that you go into work, if you're a software developer, and Monday and Tuesday, you do great work. Or maybe Monday, Tuesday, Wednesday, you do great work. But then what do you do Thursday and Friday? You do rework. Okay, that may not be such a bad thing, but that constitutes a lot of rework. The Standish group, way back in 1995, which is like dinosaur ages ago, said that the US government and business spent $81 billion on canceled software projects. $59 billion were due to budget overruns. Okay, but that was in the past, right? We've got to be better than that right now, wouldn't you think? Well, let's take a look at one of the projects that happened, an FBI project, the Federal Bureau of Investigation in the United States. They had a $170 million US dollar project, and their senior official said the program is a train wreck in slow motion. Yikes. So they actually canceled it. They said this was 2005, so presented in the 2017 symposium. 5 years after the project started, the stakeholders rejected the system when it was delivered in 2010. 5 years in the making. They said there was over-optimistic reporting. The stakeholders rejected the system even though it was compliant with the original specifications 5 years earlier. And the dream of implementing this electronic information sharing system was shattered. Wow. So they said, hang on, it was time to get serious. Let's remove these impediments. They had a congressional inquiry. Everybody went before the US Congress. The project was internalized and the FBI CIO took ownership, and they adopted Agile as the project framework. And the design was broken into 670 user stories with self-organizing teams, 45 staff instead of 300. Product owner prioritized the work. They did 2-week sprints. They demoed every sprint, and they actually succeeded. So in terms of the outcome, the rubber met the road. After a few sprints, it became possible to kind of forecast the new things. The 3-year Agile project delivered the requested system and improvements, and a success after 10 years of failure and $600 million wasted on the 2 previous aborted waterfall attempts. And so they said the total cost was only $99 million. So what does this really mean? Well, can everybody just adopt Agile? No, not necessarily. But it took a long time to realize that the project was not succeeding. There was an awful lot of money spent, $600 million wasted before getting it back on track. That's not a good situation. It's not a great success story, especially when you consider the first 10 years. So if we look at the Standish Group Chaos Report from 1996 to 2015, and there's more recent studies, but these were the best figures that I could get off the internet. Success, though, means on time and on budget with all features. So a successful project is delivered on time and on budget with all features. Well, what's that mean to software cost estimators? If you aren't a good software cost estimator, how on earth are you going to predict the future? How are we going to eventually end up being on time and on budget? Challenged projects were considered those that were delivered but were either late or over budget or missing features. And failed or canceled projects were those that had no delivery. And they've taken a look and said, okay, let's take a look at successful, challenged, and failed. Let's take a look at the comparison between Agile and Waterfall. Well, this almost seems like if I gave it more budget or more time, suddenly the project would be a success. That's not necessarily so. When we overestimate our abilities, when we underestimate, we end up with projects that are underfunded. We end up with projects that cut corners. We end up with projects that end up ultimately being in trouble. So underestimation does not cause failure, but it's definitely a contributor. PMI did a study as well, where they took a look at overall project performance metrics. This was across the board, and this was primarily for software intensive projects. So the goal, meeting the goals, doesn't seem to be a huge problem, but meeting that original budget and delivering on time and scope creep and original budgets are lost and deemed failures. These are really costly to have as failures. And we haven't improved a huge amount since the beginning of that study. So the whys of project failures, there's a lot of causes for project failures in the software industry. Number 4 is poor cost and schedule estimation. Overly optimistic and avoiding risk. If you take a look at hidden costs of going mean and lean, faster, better, stronger, cheaper. We produce unrealistic goals. We have a problem with resources. Sure, there's other problems, but cost and schedule estimation should not be contributing as factors on project failure. Tom DeMarco said a few years ago, any failure in the software area will be viewed as a direct result of underperformance, even though that's not even a significant factor in the failure of most projects. Failed projects had goals, but they were inherently unattainable because the schedules were too low, or the schedules were unrealistic, or the costs were not good. And we can go, oh, hang on, but we have to estimate at a project inception. In software projects, we have to do our estimates way up front when we first got requirements, or maybe even high-level sketchy requirements. And we can say, don't make promises here. Make them only when you know what you're actually doing. And software estimation poses some unique challenges that are just not part of hardware or facilities or other types of estimating. We have a lot of uncertainties. We've got uncertainty to do with the scope, the size of the software. We've got uncertainty to do with the non-functional requirements. How good does something have to be? The technical complexity, time, if we're doing date-driven, we're compressing the schedule. Locations and co-location of teams, the team size, rework, the ambiguity, the cost of keeping of just the status quo, and the capability and human factors. Wow, it can be a little bit overwhelming when you start talking about software. Early software estimates. There's actually, and you may be surprised, there's back of the napkin estimating, which is actual reality in some circles. So what do we deal with? We're looking at, are they fixed or fluid software requirements? Are they ambiguous? Are they complete? What about the intangible software product itself? In Agile, We talk about this WWKI, WWSI. We will know it when we see it requirements. We can start applying, even at this level on the back of a napkin, structure and knowledge. We can look at things like functional requirements, sizing, non-functional and technical. We can start doing that. Well, when I was looking at this, I thought about it and I thought, okay, what other industry actually deals with this level of estimation uncertainty? And Capers-Jones, coincidentally, said, you know what? Not only do we have all this uncertainty, but software has the worst metrics and measurement practices in human history. Wow. So I mentioned that I live in Florida. So if we take a look at Florida and hurricane forecast models, that would be an interesting thing to look at. That's got a lot of uncertainty. Hurricane forecast models, there's lots of them. There's dynamical, not dynamic, dynamical models, which sounds like to me diabolical, but that's a different story. Statistical, dynamical, and trajectory models. There's ensemble or consensus models. There's numerical models of storm surge, wave, and coastal flooding. There's a lot of uncertainties and a lot of factors that go into hurricane prediction. NOAA, the National Oceanic and Atmospheric Administration, has databases from years of historical tracking data. They've got a lot of different global models that they use. They look at forecast hours. This is a constantly changing science-based industry. They've got many science-based models and equations for forecasting and estimating the landfall of a hurricane. And yet, hurricane forecasters showing their predictions end up looking like what we call spaghetti models. Hurricane forecasting is essentially the inverse of that software estimation cone of uncertainty. Look at how many models they use. They know where they're starting. They have an exact idea of where they're starting out. You know where the hurricane is at this point in time. So that's what I mean by it's essentially the inverse of our software estimation cone of uncertainty. They know where they're at and they don't know where they're getting to. We start out in the opposite. We start out, we have no clue where we're at, but we know where we want to get to. So I found it interesting when I did a little bit more study, and you can see this if you go through the recording at the end, but I thought even with all of this incredible science behind hurricane forecast computer models, they came up and said, you know what? These models have three main sources of error. Initialization will always generate a forecast that is imperfect. In terms of resolution, they said, you know what, models are run on 3D grids, thus processors are smaller than that, such as thunderstorms aren't handled well, have to be parameterized. Parameterized, that sounds familiar. This means they have to make up parameters and fudge factors that do a good job giving the right forecast most of the time. Are you serious? A science-based prediction industry actually documents that they use fudge factors? And our basic understanding of the physics governing the atmosphere is imperfect. So the equations we're using just aren't quite right. I thought about that and I thought, okay, what can we learn from this that we can apply to software cost estimation? Well, ICEAA was looking at the same things because I'd like to introduce to you ICEAA's cost estimation body of knowledge, or the software CBOC. Why software CBOC? And this is something I just came up with, that over and under optimism leads to distrust or mistrust and the perception that software cost estimation is not a true profession. Despite the software industry having the worst metrics and the measurement practices of any other industry in human history, I think we can do better. So software CBOC is going to be an add-on to the original CBOC with ICEAA. We've got 6 major lessons that are based on the Defense Acquisition University BCF 250, which is their software cost estimation. We've got a special issue or a special lesson on software size, a special one on productivity, and one on commercial estimating models. The software size, we're going to take a look at a lot of different types of functional size, relative story point, relative effort sizing and story points, effective source lines of code. We're not getting rid of source lines of code, accounting for reused and adapted code, other considerations, rules of thumbs, questions that you as a software cost estimator should ask about software size. Not to be an expert, but questions to know whether or not the software size that you're given is valid. Software CBOC provides guidance in terms of fact-based software estimates. We can take a look at system definition, the cost drivers, issues of software growth and reuse and adapted code, COTS and packaged software, commercial off-the-shelf, sustainment and maintenance, and using estimating techniques that you've seen before, but applied to software. We're going to use multiple different types of techniques in the software CBOC. We want to make the best decision, a go, no-go conservative estimate based on data and formal practices. We're going to look at a little bit of increasing cybersecurity. What does that do to cost? And then, as you probably know, if you've got anything to do with software, the agile and agilists, the agile paradigm, they'll say, hang on, Carol, agile changes everything. You can't cost estimate agile. Really? Too many variables, inconsistent, the subject's unique? Does agile really change everything? I don't think so. So we can now improve through structured practices. Even the back of the napkin estimation can be improved so that we can end up with a size-based and data-based reality. So what do I see? I see a really bright future for software estimation. And if we get better software estimates, we've got a better chance of having project success. Software provides a number of unique challenges for the estimator. Understanding software cost estimation and the basic principles is critical because software is increasingly part of almost every program estimate. The software portion can actually delay a major program for which software may be a minor part. Solid CBOC principles apply to software CBOC with software nuances. There's changes. Paradigms, software growth, packaged solutions, they all can affect cost and schedule. And a fool with a tool is still a fool, but we can educate the fool so they're no longer a fool. Understanding cost drivers and the proper use of historical data are prerequisites to creating better estimates and better projects. We can learn to communicate with ranges and bands of uncertainty, the same way we do in other estimating industries. Software CBOC, in my opinion, is definitely a major step forward. Thank you. I appreciate your time. I appreciate you being here. And Megan, it's back to you.
Standing, thank you. Hang on one moment. Anthony, if you'd like to say a few words to introduce our second speaker, you're up.
Hello everyone, I'm Anthony March, the Deputy Chairman of SCAF, and I'm standing in for Snathan Rajagopal, who sends his apologies for today. On behalf of SCAF and ICEAA, I'm delighted to welcome our presenter today, Dr. Maryam Farsi, who is a lecturer in Through Life Engineering Optimization at Cranfield University, School of Aerospace, Transport and Manufacturing here in the UK. Dr. Farsi gained her MSc in Civil Engineering Structures from City University of London in 2010, and her PhD in Nonlinear Structural Mechanics from Imperial College in 2014. Dr. Farsi's main research focus is on complex systems and system-of-system simulation, modelling, optimization, data analytics, and data visualization. This includes enterprise and supply chain simulation optimization, product and service contracts, lifecycle cost modelling and analysis, and risk and uncertainty quantification with over 15 research works. It's my pleasure to hand over to Maryam, who will take us through an ontology-based cost modelling approach for high-value manufacturing. Over to you, Dr. Farsi.
Thank you so much. Thank you for the introduction. Hello, everyone. I hope that you're all and your family is all well and safe in this situation. I'm Maryam, and I'm a lecturer in True Life Engineering Optimization. The slides that I would like to present to you today is the outcome from an ongoing project that we have on looking at a different approach in cost estimation for the high value manufacturing, and we are working with a number of leading OEMs in the UK across the different sectors. So before I start with my presentation, I would like to have this risk of using a Mentimeter. However, I'm not going to present anything live in the slides, because I don't think if you have time for that. But I just have a question about how you find the proposed ontology-based cost modeling that I'm going to present today. So if you have any time to just search for the menti.com webpage and have the intercode of 77933024. You can give me your feedback on the presentation that I'm having today with you. Thank you for that. And okay, so let's start with a little bit of background in a way that why the proposed ontology-based cost estimation could be effective. When we are looking at high-value manufacturing sectors, we have a different complexities and challenges when we are going to do a cost estimation and predicting cost. So part of these challenges may come from the lack of complete and reliable historical data on cost element, on different cost elements. The other thing comes from a different level of uncertainties that we are facing through the cost estimation and through the product life cycle. So part of these uncertainties may comes from the uncertainties with regards to the service cost, with regards to the product itself. And some of the uncertainties comes from the complexities that we are facing with the high value equipment. So what are the services? What are the different activities on the MRO process? So some of these complexities comes from the way that we need to process with a different MRO activities and coming up with the cost of each actions. Because, for example, it starts with the MRO trigger event, it goes to the logbook, and then we have the technical reviews, we've got the work scopes, looking at the different database like Maximo or SAP data. And also at the overhaul, we have a different activities to look at. For example, in the case of an engine, we look at the engine, inspected, looking at the sentencing, and also looking at a different logistics and inventory for the spare parts, component reviewing, testing, etc., etc. So this becomes a very kind of complicated process in a way that we need to now estimate the cost of it. And also, at the same time, we need to prepare a different documents, the rejection reports, the root cause analysis, the disruption drivers, the MRO planning, looking at the rainbow analysis, FMEA and FMEK, and a reliability-centered maintenance. So these are all the things that we need to look at when we are doing the cost estimation. And each of those comes from a different database. So by this, we are going to see how the complexities comes from when we are going to look at the cost estimation, the lifecycle cost estimation of a high value equipment. Now to simplify the process and to see how the ontology approach can help us with this complex task, we would like to answer a couple of key questions. So the first questions for us is, what is the item that we are going to look at to estimate the cost? So for this, we come up with a taxonomy. So we think about, okay, is it the item, is it at the platform level? So are we, for example, going to looking at an aircraft, for example, or is it at the product level or an asset level, or are we going to looking at a specific engine type, for example? Is it at the system level? Are we going to look at any high pressure or low pressure turbine system? Is it at the commodity level or sub-assembly level? Are we going to looking at, for example, a bearing, a cost of bearing? Or is it at the feature level and to look at, for example, a ring or a flange at this step? So it is important for us to see what is the item first. And then the second question, the second key question is, how much does it cost? So we traditionally, when we were looking at the product lifecycle cost, we looked at the capital expenditure, the CapEx, and operating expenditure, the OpEx. We can also looking at this in a way that we separate the life cycle into the 4 key phases of the design, production, operation, and disposal. And maybe you're already familiar with the chart at the bottom corner, at the bottom left corner of the this slide from NATO, that it separates the different costs that we are going to looking at different stage. So for example, the design and production, the acquisition cost may comes from a different cost elements, such as the project management, the development, tooling, and so on and so forth. And we add this to some of the procurement program costs. So that's the place, for example, some costs with regards to the infrastructures or training where IP would be added. And then we looking at the cost of ownership when we are going to looking at the operation and different costs that happens through the operation and maintenance. So what are the different maintenance? What's the cost of upkeep, update? What's the cost of disposal of part or the spare parts costs? What's the cost of logistics? And then we are looking at further cost attributes in a way that, okay, so how about if we are going to reach into a certain level of availability or capability? So what's this, what is the cost of the capability? Or what is the cost of retrofit and refit as part of the operation cost? And also looking at some of the cost elements at the disposal level. Again, depends on what is our answer to the first question in terms of what the item is. We may have a different cost elements and cost drivers through the life cycle of that item. Some approach that we are going to look at in the ontology-based cost estimation is the one that NATO present in terms of the cost structure and life cycle cost. So from the NATO proposal, we are going to looking at the 3 main elements when it comes to the cost estimation. We are going to looking at the product, so the role is like an item for us, so the item itself. And then we are going to looking at different activities. What is happening? What are the key activities? What are the key events through the product life cycle? And then we are going to looking at the resources. So in terms of, for example, resource, what is the cost in terms of the manpower, or the equipment cost, or the tooling cost, or outsourcing, etc. And then having these three elements to simplify the cost architecture, we think of, okay, what are the key inputs to this simple cost model? So it is going to be the cost breakdown structure. It's going to be a range of data that I'm going to go through in this slide, and we call it a minimum data requirements, and a work breakdown structure. So the cost breakdown structure and the work breakdown structure would tell us what are the different activities. And then we are going to look at a different mechanism. So we are going to see how the activity-based cost estimation can help us with estimating the cost. And also we are going to look at the uncertainty in the data and doing a sensitivity analysis and Monte Carlo simulations to capture the uncertainty, because we are not going to go ahead with deterministic values for our cost estimation. And the output could be the results from the sensitivity and uncertainty analysis, and also the true life cost breakdown, where the most cost sits. So for the first input to this cost model, we are going to looking at the cost breakdown structure. So we come up with this as part of the outcome of the projects we are working on. We come up with this flow chart that shows a different key cost events through the life cycle of the item. So the first one is the acquire and install phase, that we are looking at the cost of design, production, and cost of acquisition of the component, assembly and installation. And then during the operation, we have the cost of operate, but if you are going to simplify that again, we are going to looking at the cost of consumables, perhaps at this stage. During the operation, we may have a different cost events like the loss opportunities. So this is like the revenue that we are losing due to the lack of utilization or availability or credibility. And also we may have a cost of disrupt, which is the cost which comes from the consequences of the failure that happens during the operation. And this is like because we fail to perform at the level that we agreed with the customer and based on the service contract. And then we are going to looking at the monitor and support cost, which is going to looking at like some of the baseline maintenance and some of the regular monitoring and the standby costs, and also the cost of different investigation. Again, some of this investigation may comes from a different monitoring activities. It may raised by the customer, or it might comes from when the item failed. So if for any of the reasons, such as looking at some of the symptoms, or during the operation, or based on some policies, or for any reason that the item failed to operate, we go to the remove and inspect phase, when we are going to looking at the cost of removing the item and inspecting it. For the high value equipment, this is the stage that perhaps the item would be overhauled, and we are going to looking at that item, the overhaul. And then we go to the cost, the event of reject, that whether we decide based on the inspection results, whether we are going to repair the item or replace the item. So if we replace it, we are going to have the disposal cost for that item, and then we get back to, well, we reinstall it and reassembling it, and then we will get back to the operation. So for the work breakdown structure at the second inputs to that cost model, we're looking at a high-level works that happening at each event. For example, for the acquire and install, the work, the activities, the key activities is the acquire, the assembly, the testing, the transport, and install. I'm not going to go through the whole table, but this is like a high-level work breakdown that we can have for different cost events through the life cycle of the product or the item. So then we have the minimum data requirements. So what are the minimum data requirements? So it starts with some of the parameters that we can capture during the overhaul. So the first one is the time between the overhaul or the time between the failures. So at the overhaul, whether what is the time between the overhaul opportunities or the time between failures, and for the parent product that contains that child item. So it means that how many times or what is a time between the opportunities or the events that we need to looking at some of the components level or system levels if, for example, we need to overhaul the whole aircraft. And then at the overhaul, after the overhaul opportunities, we are interested to know how many times we do the remove and inspect. So is that the item inspection rate at each overhaul opportunity? So this is the rate basically we are inspecting the item at the overhaul opportunities. And this means that we are not necessarily looking at all the child item when we are going to overhaul a parent item. So it means, for example, how many times we are looking at like the high pressure turbine when we are overhauling the aircraft. So this is the rate. And then the 1 minus this removal rate is the other path that we go through this flowchart. And after that, for the remove, after the remove and inspect, we are interested to know what's the reject rate. So what is the probability that we are going, that the inspected item is rejected, so we can't really repair it or replace it. So if it is a reject, how many times we are going through the replacement strategy and how many times you are going to the repair strategy. So in summary, the minimum data requirement for us is the time between the overhaul, is the removal rate, is the rejection rate, and the replace rate. And there is another item in this minimum data requirement that we call it the overhaul inspection interval, which comes from the ratio between the time between overhauls and the removal rate. So it is the time between the inspection of the item when the parent item is overhauled. So with this, we've got our 3 inputs to our cost model. Now, when it comes to the estimating the cost, in this ontology-based structure, we are proposing the activity-based cost estimation. And the activity-based cost estimation looking at 2 main inputs, looking at the unit cost of events and the quantity of the events, and by multiplying the quantity by the unit cost, we are coming to the subtotal cost of each event, and then we sum it all together, so we have the total cost. So some of the frequencies can comes from the minimum data requirement, as you can see in the table on the left-hand side. So we can calculate the frequency of the remove and inspect event, the reinstall, reject, replacement, and repair strategy event. based on the data we have for the minimum data requirement. We also need the frequency to the other events to estimate the cost. And of course, we need the unit cost or the standard cost for each event. And after that, by using the activity-based cost estimation, we are calculating the cost of the item through the life cycle. And bear in mind that having a different item at different levels, we have a different cost drivers and the cost elements. So basically, we are not going to looking at the whole cost activity or the cost breakdown and structures for all the type of items at all the levels. The other things that we would like to look at in this approach is the uncertainty. So we are looking at how the uncertainty from the minimum data requirement propagates to the frequencies and also to the frequencies and then number of events and also the uncertainty from the unit cost, how it propagates to the cost of event and finally to the life cycle cost. And then to create our ontology, we look at two main databases, the database for the item and the database for the cost event. So the database for the item includes different multiple subclasses. So how the asset or the parent level would link to the component level or the child item. And also another attributes to that, for example, how many child items we've got in that parent item. And in terms of the cost event, we are looking at a different phase. What are the different events in that phase and what are the different activities in that phase? And two key attributes, the properties that we are looking at is the unit cost and the frequency of that activities. So we've tested the approach in a case study of a machine tool. So this table shows the first table in the middle shows the assumptions for the minimum data requirements, and the detailed table on the right hand side shows the unit cost and the frequencies over the 30 years life cycle for that machine tool. And then we estimate, we go through the activity-based costing to estimate the cost of each event. So we use the protege also to create this ontology. So this ontology shows where each activity sits across the life cycle and what is the item and how the item links to the different cost activities. And this protege links to the data that we had from this machine tool case study. So each time if you are going to, for example, add any activity or add any event, this ontology will be updated automatically for us to show a different cost elements through the life cycle of that case study. And by estimating the cost, we come up with the different outcomes. For example, we've looked at okay, what's the relative impacts of the, for example, 5% sensitivity variation on the data. So what would it look like if we add a 5% variation to all the unit cost and the frequencies, and which one is more sensitive, which cost event is more sensitive to that. And you can see in the pie chart that, for example, the replace cost is the most sensitive cost event. And you can see by 5% sensitive variation to the cost elements, you have about 65% variation in the replace cost. And the other outcome we can get from this approach is, for example, we have a deterministic sensitivity analysis with that 5% variation to see, okay, in terms of the cost, how the cost would be different, how the cost of different events would be changed if we have this variation across the cost elements. And also at the top, you can see the probability distribution of the probability distribution function for the total life cycle cost. That it shows basically if we put a 3-point estimation to the unit costs of each cost event, what would be the distribution of the total life cycle cost, and what would be the most likely or the mode value for the total life cycle cost. The other outcome we get from this approach was to see where the cost sits across the life cycle and different cost events. And it shows like a heat map that shows that, for example, what event costs more across the life cycle. The other things that we've added into it that we integrated with the customization for servitization types contracts, the product service contracts. So we just translate the whole the cost breakdown structures into an object-oriented programming to create this flow chart, and we run it for the 30 years. So the outcome of this also told us about what type of the service cost would be most beneficial for us. So, for example, it told us like the uncertainty in cost estimate in the cost estimates of the service contracts for the new products or the products which are close to the end of life has more variation and has more uncertainties compared to the cost estimates for the middle-aged products, or the overall uncertainty in benefit estimates in availability-based contracts would be higher than the spare parts contracts. The other type of outcome that we get out of this type of analysis is, for example, we've done a radar analysis to show for a product age of between 1 and 15 years. And if you're looking at, for example, a 15 years contract, the availability-based contracts is going to be more profitable compared to the spare part contracts. Or in the other graph, you can see, for example, how the number of failures and failure rate and the scheduled maintenance can affect the profitability. In what range our contract is not going to be more profitable anymore. Yeah, so these was the type of different outcomes that we got from that analysis. And that was my presentation. Thank you.
Awesome, thank you. We'll we've got just a few moments for some questions. Peter Moreland, you had one. I'm hoping you're ready to ask. If you are, you may go ahead. All right, this is a question for Carol. What is or are the underlying drivers of the estimate, the lines of code? How do we establish how many lines of code are required as Agile links to functionality and features or pulses rather than code? Can we link to that? I'm sorry if I've butchered the question. But.
No, that's totally fine. One of the things that we've discovered is while Agile ends up being a flexible scope, we need to have estimates upfront based on typically very, very high level estimates of what the size may include. So while traditional predictive waterfall type projects start out with a fixed scope and then have a variable cost and schedule, it's kind of the opposite when we do Agile. We may still do a similar type way of estimating the size, but it's very, very high level, where then we do the estimate of the cost and the schedule. The cost and the schedule then become fixed, and it is the scope that becomes variable based on our product owners prioritizing and changing the requirements, adding new requirements, and having that level of flexibility. So my source lines of code, if I can find some good historical data on which to base my original estimate, I can do that original estimate. But then as the project progresses, I can only deliver or actually measure source lines of code once they've been delivered. So I don't know if that answers your question or not. I may have butchered the answer, Megan.
Well, we'll just have to hope for the best. I'm just gonna say just a couple of words to give anybody in the audience. We've got a couple minutes left. If you want to send another question, you may do so. Please use your chat box to send us more questions. But in case we don't get them, please join us next week for the fourth and final of the 2020 SCAF ICEAA virtual workshops. Anthony, do you have any closing words in case we don't?
Just thank you everyone for listening in. I hope it's been useful for you. And obviously, I'll let Megan sell next week's or 2 weeks' time.
Yes, we'll see you. Looks like so everybody, if you didn't get a chance to get any of the contact information for today's presenters, you can reach out to my office at ICEAA at ICEAonline.org, or reach out to SCAF and we'll all be happy to connect you. Otherwise, it looks like it's 1 minute left in the hour, so we'll wrap it up. Thank you all. Be good to yourselves. Stay safe and sane out there, and have a great week. We'll talk to you next week.